Good evening and welcome everybody. This is Obi-Wan Pez for and Simplex Pachinko. We are doing a special stream tonight because I had started a problem last night that I did not finish, and it was like almost 4 in the morning, so I was like, Alright, so for anybody who was not here, we were talking about completing a linear programming problem using the simplex method, not named after me. And I had to find a similar example, which then I could actually understand how this particular version of the simplex method works, because in all of the ones that I had done, we were always trying to maximize. Yeah, we were always trying to maximize the objective function, z, given all of the inequalities as conditions. Those inequalities I have now transferred into equalities, or equations, here. So these three. In this particular version, this is a minimization of the z objective function given all of these particular given these, which again were inequalities, and what I did was I made them these all had to be greater than or equal to each of these numbers. So we're trying to minimize the cost, $3, $2, $3 for ABC respectively. And you have to have these particular nutrients in your diet, at least 8 vitamins, 9 minerals, and 10 calories, you know, whatever nonsense units these are. And so we had to have, again, greater than or equal to 8, 9, and 10 for those, and also minimizing our cost. So the way to do this, and this is going to take a little bit of review for anybody who's never seen this before. The way to do this is actually to turn it into a maximization problem of inequalities that are less than or equal to all of the given conditions. So, yay! What we have to do is create this particular setup. Again, our slack variables are going to be the things that turn our inequalities into equalities. And we can find out what values those have as we go on through this. So the first thing we do with a minimization problem is to turn it into a maximization problem on slightly different variables. So we come in here and we say, now this would have looked like, right, A, B, C. We have 1 and 1 and 2 from our 3 equations or inequalities. We have B is 2, 1, 1, 2, 1, 1, and C is 2, 1, 2, 2, 1, 2. Nutrients are 8, 9, and 10, and our Z objective function would end up being 3A, 2B, 3C, and 0 nutrients, because nutrients doesn't factor into cost. Okay, then we find the dual of this, which turns it into a maximization problem. So it's the transpose of this particular matrix, essentially, that we've created here, which looks like this. So our A, B, and C and nutrients become the rows rather than the columns, and our new variables, x1, x2, x3, all become our columns. Hey, Zach! Hope I'm not stepping on Don's toes too much, but everybody can watch all of them. It's fun. But anyway, so we're creating a linear programming. I'm trying to solve a linear programming problem for Satisfactory, and yeah, I finished around 3:30 last night, and I was like, this morning, whatever. It's like, I went too late. But Satisfactory also does that to you. So again, we create these duals, which will now turn our minimization problem into a maximization problem. So we end up with this dual here, and then we say, okay, our z function is going to be 8x1 plus 9x2 plus 10x3, and then we have these inequalities, which are now going to be all less than or equal to our respective 3, 2, 2, but 3, 2, 3. Oh no. No, we're good. We're good. That could have been really bad. But good news, I didn't actually change anything. It actually was kept correct in the tableau. Okay, so we said let's create the simplex tableau where we're going to take all of the inequalities and turn them into equations by introducing our slack variables. So the slack variables are the leftover bit that we need to add in order to make our inequalities into an equality. Ooh, I like that one. Good choice of song. So then our simplex tableau becomes this. We have our x1, x2, x3 columns and s1, s2, s3 columns for our slack variables. A z star column, which is our new objective function. Again, z star is 8x1 plus 9x2 plus 10x3. And then we have to figure out how to basically use row reduce operations in the same way that you would for like trying to create a row reduced echelon form. But in this case, what we're doing is we're saying that we would like to go around the edge of the particular graph we've created here. Now, granted, this is in 5 dimensions, so I'm going to simplify it to 2. But basically, what we've done here is we've created these massive hyperplanes that are going to bound our particular region. We know that all of our stuff here, the numbers of jobs that need to be done, or no, sorry, we're still doing the nutrient problem. So the nutrient problem actually is in 3 dimensions with planes that are bounding the solutions. So we have a region, a space, there we go. We have a 3-dimensional space that is bounded by planes, which must have A, B, and C values which are greater than or equal to 0. So we can have zeros. You can not use one of these things. That's perfectly fine. For anybody who didn't catch it all the way back at the beginning, this was saying that we had to have a diet containing at least 8 vitamins, 9 minerals, and 10 calories of whatever nonsense unit this is, at a cost of food A at $3 a unit, food B at $2 a unit, and food C at $3 a unit, with these particular nutrient distributions. So realistically, what we've done is we've gone from taking our original problem, which looked something like this, and say we want everything to be greater than or equal to, our nutrients have to be greater than or equal to our 2 lines here and our axes here. And we want to basically say the only possible solutions are going to be the intersection points of each of the individual lines. Because if we move ever so slightly off of one of these points, it's going to introduce slack, which is unused stuff, which is basically just a waste of money. And then we just have to slide over to the next point. And it has to be one of these 3 points. That's it. So in terms of what we're doing, we're trying to say, like, okay, given even more conditions and even more variables and things like that, how do we slide from one position to another in an appropriate and mathematically valid way? All right, and we have now gone to the new problem, which is, since we introduced the less than or equal to conditions, everything must be on the inside of these conditions, which also includes greater than or equal to 0 in all these here. So now our points are slightly more numerous. We have 0, which realistically doesn't mean anything for us. We also have these up here and over here. So now we have to determine, we're going to start from 0. Are we going up or are we going right to get to the next particular point that we're trying to check? That way. Right or up. So the way that we do that in the minimization problems, like this one here, is we're going to say we want to look for the condition or the term in the z equation, which is going to be all the way at the bottom, z star, the objective equation. It's the only one that should have z in it at this point. Look for the one that's the most negative. So we have a negative 10. Then we say, look at the rows, and we say this number here is going to be divided into this number here. So our 3 over there on the right is going to be divided by 2. We get 1.5, 3 halves, and we're looking for the one that has the lowest ratio. So here 2 to 1 is eliminated because we already have something lower, and here 3 to 2 is going to be the same as the other one. I don't think it matters where you go from here. Like, either of those is going to be valid, I think. So rather than go to, another and then another to try to figure out what's going to be the best, like if we went to second place, right, we go to 9, and then we do the same division, and we get the same numbers. So those are still tied, and we go to -8, and then we have here 3 halves and 3. So the best one to pick would be row 3, I guess. I don't know if that is mathematically valid, but it's probably better than what I'm doing, which is I'm just going to pick one. Whichever one looks nicer for me. And I don't think I cared in this case. So I said, okay, we want to... First of all, we've chosen... row 3, kind of arbitrarily at this point. But again, row 1 and row 3 were tied. So, shrug. So I chose row 3 to be our pivot. So we're going to pivot around this point, which means this needs to be a 1, and everything above and below it needs to be a 0. So, again, row-reduced echelon form is what this is basically modeled after. It's going to be slightly different. It's not going to be in, like, echelon form, where it's going to be, 1 with a bunch of zeros after it and a bunch of zeros under it, and then diagonal to a 1 and diagonal to a 1, and everything else is zeros. Not going to happen this time, but oh well. So what we're doing is we're going to say, all right, row 3 just needs to be multiplied by a half to get this to be a 1. Fair enough. We could subtract row 3 from row 1 to clear out the 2 and make it a 0. And we could subtract half of row 3, so what row 3 is going to become, in order to get rid of this one. We can also then add 5 row 3 to the bottom to get rid of our -10. When we do that, we get this thing. We got a 1, we got zeros above and below, and then everything else is a consequence of what just happened. All right, then we repeat. So we look for the thing with the most negative number. There's only one left, it's -4. We choose that column, and then we go up again, and we choose this stuff divided into our cost over here to determine which row is going to get us the best. So again, we're going to do 3 halves over a half is 3. 1 half over a half is 1. So that's the smallest number. Go with that one. So we select this as our pivot element. We're going to multiply that row by 2 in order to get that 1 half to become 1. And we're also just going to subtract row 2 and row 3 directly in order to make this a 0. Doesn't technically matter which way is which, but again, we're just saying like, okay, keep row 3 as it is, and then subtract row 2 from it, and that gets us our 0 here. And then we get our, again, 0, 1, 0, 0, 0, 1. There are no more negatives anywhere in the bottom. So this is done. If we were doing this as a maximization, yes? If we were doing this as a maximization with conditions being less than or equal to all of these things, as we talked about up above, if that were the end game, we would look at this and say, okay, out of x1, s2, and s3, if any of them are anything other than 0, and again, they must be positive or they must be non-negative. If x1, s2, or s3 are non-zero, then it diminishes from z. So the value of z is going to be 19, according to this tableau. If x1, s2, and s3 are anything other than 0, then the value of z itself is going to be less than 19. So let x1, s1, and s2 be 0, and it knocks them out completely, and then we get x2, x3, and s1 have some sort of value, which we are going to try to find. And it's listed in here. Right, S1, since x1 and s3 are 0, then s1 is 0, also 0. So, good enough for us, right? Doesn't matter. x2, again, x1, s2 and s3 are 0, so x2 is 1. And again, x3, that's 0, is also 1. So x2, x3 are both 1. And that would be our solution. So we would look for the point where x1 is 0, x2 is 1, and x3 is 1. So 0, 1, 1. So we go back to our graph, which would, again, be in 3 dimensions, and we find that point 0, 1, 1, and it would be one of the vertices of our space, 3-dimensional space. So 0, 1, 1 would correspond with, like, this point on the plane where it is right now. So be like, we'd have x1 here, x2 here, and x3 here. So we would get that point 0, 1, 1. Okay. Now, that would be the solution if this were a maximization of z, z star, right? I should have... Again, I was doing this at like 3:30 in the morning, so... maximize z star. But that wasn't the original question. The original question was, we need to minimize z, the original z, that was then based on all of this stuff and our previous inequalities. So these were all, not these, these. We needed all of these things to be greater than or equal to 8, 9, 10 respectively. But now we created this transpose, did this whole thing with x1, x2, x3, like what the hell is going on here? So, the interesting thing, it's really weird, the really weird thing about this is that our solution is the slack variables. Our solution to the original problem is the slack variables. When we take those, 0, 8, 1, we end up with 0a plus 8b plus c. Let's clean that up a bit. All right, and we look at the original problem. Our cost, z, was going to be equal to 3a plus 2b plus 3c, which gets us 0 plus 16 plus 3. I'm okay. Right? Oh, that's not that. This is a equals 0. B equals, there we go. Equals 8. C equals 1. And Z is equal to $19 in this particular case. So this gets us our solution, the thing we're looking for. It gets us our Z, the maximized Z value that we could find in the previous one, or maximized Z star, anyway. And if we look at the original inequalities, we were looking at the amount of nutrients you get from each of these things. So again, hey Ben, we would get 0a, so that would get us 0, 0, 0. 8b is 16, 8, right, that's this. A. Right, 16, 8, and 8 for B, and 2, 1, 2 for C, which, again, get us our column values of 18 vitamins, 9 minerals, and 10 calories, again, in whatever nonsense units we're using. So we've gone way above on vitamin, and then mineral and caloric content are exactly on the money for what we wanted. And we appear to have minimized the cost at $19. So we could try to find some other solutions, potentially, but, you know, I don't think we're going to find anything better. It should not, in fact, find anything better. This should be it. So, if we apply the same thinking to our actual satisfactory problem, this is in 5 dimensions, so it is going to be bigger. Our objective function is going to be to maximize the amount of smart plate we can get. And we're going to use these conditions here to tell us what we're going to have. So we need... right, we can trade 30 ingots for 20 plates. We can trade 15 ingots for 15 rods. We can trade 10 screws for, 10 rods for 40 screws, and 20 rods for 100 screws. And trade 20 rods, 100 screws for 1 rotor, and 30 plates and 60 screws for 1 reinforced plate. At the end, we need to make 2 rotors and 2 reinforced plates in order to get 1 smart plate in 1 minute. So I'm looking at the throughput of my factory. I was trying to figure this out. Trying to figure this out in terms of, like, how all of this is going to work. I am less confident right now that this is actually what I want, but yep. So I was trying to figure out how many jobs of each assembler, whatever the things are. I have my notes here. I probably left it downstairs now that I'm thinking about it. Yeah, I did. How many constructors, assemblers I'm going to need in order to create all of this stuff in the appropriate short amount of time. I have 1 minute, well, the throughput, right, is per minute. So I want to be able to create this amount of stuff in 1 minute, and I need at least a certain number of constructors or assemblers in order to do each of these things. So we'll see how it goes. And I'm trying to figure out, like, what would be the appropriate inequalities that we have as constraints, right? So I need our smart plate is the objective function, which is going to be equal to the number of rotors plus the number of reinforced plate that we need for these things. So this is a terrible variable system, but I don't even care. And then, so here's the thing, right? These are technically, these exchange rates are fixed. Yeah. So all of this stuff must be non-negative. In theory, I could have zeros somewhere, but I can't, right? We know that it's not possible to have zeros for any of this because we need all of these things. And then I was thinking, like, is it actually linear programming, or is it just, like, could we just get row reduced? But I see. No. So in this particular case, the smart plate is equal to 2 rotors plus 2 reinforced, right? The 1 reinforced is equal to 60 screws plus 30 plates. But the thing that happens with linear programming is that we shove all the variables to one side. Yeah. So if this is appropriate and if this actually works, I don't know that it does actually, now that I'm, like, you know, now that I'm doing this, right? I don't know that it's actually... right. So, I mean, like, maybe I'm just using it completely inappropriately. It could also be that I just need to talk about it in terms of the number of, like, the number of jobs that are being done, rather than the exchange of materials. Voting day in Canada! Woo! Aye, please, everybody vote. Have your opinions be heard, even if you don't like it. It is still important that everybody do it. In theory, I have a ballot in the mail. Mm-hmm. Yep, very nice. What'd you get? Apart from a I voted sticker. kettle chips and a peach whip beer. Nice. I mean, everybody gets a sticker, right? While supplies last. I mean, you gotta give them to, like, the 5-year-olds who are accompanying their parents, but nonetheless. More personalized, yeah. Do you mean a mug club membership that has a mug with your name on it? Because that could work. See, I've got good ideas. So yeah, I'm actually kind of wondering if we just need not this. If I just need to literally enter this as wait. Okay. So I'm wondering if I need to do this as the sums of all of the columns. Sort of. So, like, ingots, plates, rods. Right, the number of ingots that are produced every minute is, of course I can't remember what it is now, but alright, let's look up Satisfactory. Building production. I don't really care what version we're using on the miner. I've never had a problem with miners. Constructor. Excuse me? Machines. There we go. Constructor. Oh, okay. Iron ingot. Items per minute. Oh, great. This is not what I want. Just get me the raw production information. Buildings. Satisfactory wiki. Thank you. Nudge. Oh, H and arrow keys. Interesting. Assembler, but not assembler. Or rather, I also want the assembler. Smart plating. Reinforced iron plate. Okay. Open iron rod. It can be created in crafting constructor. There we go. Alright, in the constructor, we can create iron. No. We can create iron ingots in the smelter. There we go. Okay, here we go. So, iron ingot, you can create 30 per minute. Okay, that is literally what I wrote on here. So all of these are per minute. Okay, so you've got 30 times the number of smelters. Which then needs to be greater than or equal to our total necessary usage of ingots, which is going to be 45. Right, so through plates and rods, we need at least 45 ingots per minute times the number of whatever else we need going down the line. Alright, plate. Boy, we need 30 per minute to go into reinforced. So this is the number of assemblers. Must be greater than or equal to. We need 2. Hang on. There's our smart plate. So that's actually 2 as well. Man. Technically that reduces, but that's not the point. Right? Reinforced plate is done once every... for God's sake. Alright. Okay. So here, it's going to be 45. We got 30 times the number of assemblers is plate. it needs to be greater than or equal to... No. Production. It's going to be 20 times the number of constructors devoted to plate. Must be greater than or equal to 30 times the number of assemblers devoted to reinforced plating. So because of that, this is wrong too. Okay. Things that make... Those are smelters. They'll do 30 per minute. It's not 45 though, it's the number of... Right, so this is going to be 30 times... Must be greater than or equal to 30 times the number of devoted constructors to plate plus constructors to rods 15 times. Maybe that's just wrong. If you guys see anything that I'm blatantly doing wrong, let me know. The number of rods produced is 15 times the number of constructors devoted to rods, which must be greater than or equal to the things that use them. 10 times the number devoted to screws. That's probably not correct, now that I'm thinking about it. Constructors to screws. Plus 20 times the number of constructors devoted to rotors, assemblers. Nope. Assemblers devoted to rotors. Screws. Can produce at a rate of $40 a minute. Yeah. 40 times the number of constructors devoted to screws. Yeah. Must be greater than or equal to. The usage is off the chart for this stuff, so hooray. 100 times the number of assemblers devoted to rotors plus 60 times the number of assemblers devoted to plate. Ugh. Rotors. Will produce 4 a minute. Oop. Yeah. So... 4 times the number of assemblers devoted to rotors must be greater than or equal to the number of smart plates we get, which is 2. Two times the number of smart plates we get. Assembler. Smart. Reinforced plating is created at a rate of 5 per minute. Must be greater than or equal to, again, 2 times the number of assemblers we get for smart plate. I mean, I know that that's basically just true itself, but what do we want with this, really? How much plate per minute are we going to use to make smart plate? It's just 2 a minute for both rotors and reinforced plate. So in theory, right, this is the nastiness that we get for all this. Right, the ratio there is 1 to 1. 1 to 1 to 1. On reinforced plate and rotors becoming smart plating. Granted, it's 2 a minute, but that's not the point. We're trying to maximize the number of smart plate we can get out of this. But these are not less than or equal to. What is this? These constraints are not what I was expecting.
You close your eyes against the glare of this Atlantic sun. You've reached the edge. There's nowhere else to run. So you take your boat and wait for a wave to carry you away. You hope you'll make it home.
In theory, what we're looking to do is minimize... Okay, I got it. what we're actually looking to do is minimize the number of machines. Realistically, right? We also realistically want all of these to be... We want all of these to be integers. Right. And there's no actual, like, cost value in here, or constant value that we're going to get in all of these cases. So that is wild. So if we're minimizing, we've got all these constraints which are greater than or equal to, which is going to create probably a bit of a problem. This is fine. So, smelter, plate, rod. Screw. Alright. Just take it down there. Constructor for screw. Constructor for rod. Constructor for plate. Assembler for rotor. Assembler for reinforced plate. Assembler for smart plate. Maybe. Oh no. I kinda hate it. We'll see if this is even viable. Real quick. So 30. Negative 30. Rod. That's this. Negative 15. 0, 0, 0, 0. And whatever this would have been, but constant, right? There's just literally nothing here to use. This one's going to be 20 CP minus AP 30. P. Okay, zeros everywhere else. Uh, 15 rod minus 10 screw minus 20 AR. Zeros elsewhere. Screws are going to be at 40. Minus 100. Minus 60. Yep. Zeros elsewhere. Oh, man. This is fine. No, this can't work because I'm going to have zeros all along the bottom. Because there's no constant. There's no constant value, which means there is no objective function to the dual. Uh-oh. I just backed myself into a big corner. That's a bit of a problem. And there's something, right? There's got to be something. Well, you know what? Let's see if miraculously this is going to produce some sort of reduced echelon form, which is going to be decently nice. So this is 4 AR with -2 AS. And 5 AP for -2 AS. Yeah. Thanks, Michael Morph. Next question. Where's my calculator? Yep, there it is. So if we go with matrix edit, how many rows and columns do we have? We have 1, 2, 3, 4, 5, 6 by should be 6, 7. Cool. The number of each particular building that's required in Satisfactory. Ooh. Yep. 15, 10, which I know is probably not the right way to do this, but I don't know. Let's just suppose this is the proper way to do this for a second and hope. There is in fact a solution to this using row reduced echelon form, which is 1, 0, 0, 0, 0, 0.05, which I'm going to multiply all these up in a minute here. Or figure out what the meaning of all of this is going to be. But nonetheless, there is an actual... No, okay, never mind. There's negative numbers in here too. Cool. Alright, ads are just about to start up. We'll have a discussion about this in 3-ish minutes and figure out what exactly I'm doing wrong, because there's probably a lot, but it's fine. I mean, fair enough. Alright, see everybody in 3 minutes. Be right back. Hey, Syntax, if you can hear me. I know some people are still on ads, so sure, I can help out with ODEs as well. We're just trying to solve this for my own personal benefit. Alright, welcome back, everybody. So, yeah, Syntax asked a question. We will be glad to also do whatever other math we feel like. I'm just doing this for my own benefit because I'm trying to figure something out for my factory in Satisfactory, but definitely, we'll just move on. Screws. This is rotors. Two rotors. Oops, assembler rotor. So -1 AS. And then 5 assembler plate is going to be equal to 4 assembler smart plate. I don't think these numbers are right either, but solution given in the initial conditions cannot be reached from your general solution. Yeah, it seems like a problem. Definitely. We'll check it out. Okay, so we're in pens. Discord. Sorry, I was just typing out something else. Do. Don't mind me.
That trademark place.
Okay. Oh dear. Okay, so it's a nonlinear differential equation, first of all. So that's maybe a bit harder to work with. But you're saying that you have a second order differential equation that's got a y cubed attached to it. Y cubed times y double prime plus 1 is equal to 0, where y at 1 is 2, y prime at 1 is negative 1/2. No. The nonlinearity of it isn't necessarily going to be an issue in any way, shape, or form, but it does potentially cause some frustration as we go through it. So you said, let's take this. Yoink. Downloads. Yeah, that's good enough. Oh boy. Okay, so subtract both sides by 1. Isolate our terms. Alright, fair enough. Then you've got... Oh. Okay, you did fix it. Right. Yeah. Derive or take the antiderivative of both sides after multiplying both sides by y prime. Fair enough. Mm-hmm. Okay, so one of the things that you would probably want to just double check is to see whether your constants have stayed mathematically equivalent the whole way through. So like, right, if you've got a C here, okay, so one thing here, how did your 2 go from the top to the bottom? Top 2 was just a mistake overall. Yep, okay. Yep, that's fair. Right, because we're dividing by the new exponent. Cool. Okay, then you multiply by 2 all the way through. That doesn't change the fact that this is a constant, right? So we're good there. So again, if you did something that involved like finding out what that C value might be, there is the possibility that you like backed yourself into a corner here, but you're fine. You could actually find the value of C here. Alright, so if we go y prime at 1 squared over 2, that should be equal to 1 over 2 times y at 1, all plus c. So this is going to get us a negative 1/2 squared is a positive 1/4, divided by 2 is going to be 1/8, equals 1 over 2 times 2 plus c. That's going to be 1/4 plus c. So your c value should be a negative 1/8. Yeah, if you do stuff ahead of time, it can save you some hassle later. And the other problem is that, right, because this is a plus or minus, there's like the possibility that trying to plug things in at the end could like give you a non-functional solution, or you could end up with 2 particular values. But in this case, if we solve for C like as soon as we can, as soon as it's viable, then we have a number tagging along instead of variable. So you don't have to solve a 2x2 system of equations later. Or try to derive it again, because no. Right, just no. that's oh, that's nasty. Yeah. Yep. Because again, realistically, what you've got is the absolute value of this thing is equal to the square root, and then you took out the absolute value and just made it plus minus, which is fine, right? Like normally it's equivalent. You just have to sometimes be careful. But yeah, try it from there. See if you can find k given that c is negative 1/8. What's going on there? Something does not like my computer right now. What is going on? Maybe it's just Discord. I can't click anything. I can right click, but I can't left click. Nothing's holding down my buttons. Bizarre. Okay. Something's wrong. So like I can left click on my windows and it switches windows, but I can't actually left click on Discord. Like it's throwing an absolute tantrum. Hang on. Well, I could right click and close Discords. So that's one way to go. I still can't left click in Discord. That is so bizarre. like the mouse will highlight stuff if I'm sitting over it, and it switches its window, or it switches its, like the picture. So bizarre. Alright. And I can write. Not that I want to write with my mouse, but still can't do it. Alright. So what do we got? So if we let this be negative 1/8 here, so, right, you're multiplying y on top and bottom. That y becomes y squared on the inside, which then knocks this out here. This is going to be a negative y squared over 8. Or we could likewise multiply by 60... No. Square root of 8 on the outside. That'll get rid of... Right. Turn this into an 8. Make that still minus. We'd end up with a root 8 outside. Trig. No, we don't need it because we've got a y up top. Never mind. U sub. Right. We'd have a negative root 8 du, where u is equal to y squared. So du would be equal to 2y dy. We need then a 2 here and here. Okay. So we've thoroughly messed this up pretty nice. 2 over root 8 minus u squared. Equals plus or minus 1. Oh, sorry, that's not u squared, that's u. There you go. That negative has been absorbed into the du, so that's not there anymore. So negative root 8 over 2 times, this is going to be the square root of 8 minus u over a half, positive a half. It's going to be equal to the integral dx. It's going to be plus or minus, this is going to be kind of gross here, but yeah, you get the plus or minus x. Alright, the 2 and the 1/2 are going to make 1. Plus c, or plus k you did, so that works for me. Okay. root 8 times root 8 minus u, which is now y squared, right? We can bump that back. Is equal to plus or minus x plus k. And then you have 1, right? Y at 1 is 2. So negative root 8 times root 8 minus 2 squared. Hey, that's actually a nice number. It's plus or minus 1 plus k. So, should work. The whole inside? Sure. The 8 is just a subtracted value, so clears out when you do du. If that's what you mean. Actually, is that off by a negative? No, we're good. Okay, sorry. This negative technically is still here. We balanced it with a negative outside. It gets absorbed into this larger integral here. It just becomes this other stuff. That's fine. Right. The negative on the outside is a balance. The c was negative 1/8. And then we did some clever multiplication to get rid of our denominators in both cases. So that's going to get us a root 8 on the outside. It's going to be an 8 on the inside. Clears out the fraction. Y on the outside becomes a y squared on the inside. Clears out that fraction. And so we get both of those things. Right, you got your 2y on top to balance out, then y squared at the bottom here to become, that's fine. So the expression on the inside doesn't change. Right, when you take a derivative of the quadratic on the inside, it stays that value all the way through. Like you've got your whatever x squared in there. It's just the same as doing our I don't think I understand what you're saying. When you take the square root of something with an expression on the inside, then you're looking, by chain rule, you're looking for doing the antiderivative of the overall. You're looking for the solution or the derivative for the antiderivative for the overall function, which in this case is the square root, and the denominator, or negative 1/2 exponent. When you take its antiderivative, it's a positive 1/2 exponent. The stuff on the inside doesn't change. My goodness. Right? So what we should get then is that k is going to be equal to a 1 plus or minus. That's not true. It's a plus or minus, but that's on the 1 itself. We've got now a negative root 8 times 8 minus 4 is 4, which gets us a 2, plus or minus 1. So 2 root 8 is 4 root 2. Negative 4 root 2 plus or minus 1. So you're saying that y should be equal to square root 6 minus 2x. Alright, y prime is going to be equal to 1/2 times 6 minus 2x to the negative 1/2 times negative 2, which is going to be the derivative of the inside. That gets rid of that, and then we can just stick the negative on the front. Take y double prime, that's going to be equal to negative 1/2 comes down and interacts with that, makes it positive 1/2 times 6 minus 2x to the negative 3/2, and then times negative 2 again. So this gets rid of that, and again we get the negative coming out front. So this says that we've got a 6 minus 2x to the 3/2 is going to be multiplied by the thing we have underneath, which is a negative 6 minus 2x to the negative 3/2 plus 1 equals 0. So that actually does look right. Right, so we get a negative 1 plus 1 is equal to 0. Alright, seems right. So how'd this go, right? That's the next question. Nice megamorph. I know that 8-bit D has that as one of her sound alerts. She loves that one. It's a whole song. It's gotta be a meme that I just don't know. Okay. Yep. So where did it go wrong, huh? So this is also an interesting part of like differential equations in general, is that you should have two linearly independent solutions to this because you have a second order differential equation. So it's very possible you have just found both here. How did Dawn do math? How did Dawn do the solution for that one? No idea. Okay. Oh, not second order. Okay, fine. Fine. Right, so if we do it by separability, that's what we've got. Right, so that all that stuff can be worked around like that. Sure, it's not that evil. No, I didn't forget the +1, but I can't do anything with it right now as it is. The +1's right there. I was just seeing if it like unlocked any memories for me here, but no, not really. Okay. Double prime times y cubed plus 1 is equal to 0. Y prime is equal to -1. So if we just went with it as it is, without messing around with anything, no, we can't do that. Yeah. I mean, I think yours is just like the easiest way to think about that in order to make sure that you got both parts. So when you did this, you had y prime, y double prime is equal to y prime over y cubed. Right, so then negative. So yeah, here is going to be y prime times y prime prime. So take that integral and you do end up with gets absorbed, and so it just goes into there, and then it's just plus C. Yeah. It's like I'm not sure how we would go and get that particular solution. Just the square root of 6 minus 2x. Unless that is oddly and specifically identical to the actual solution that we got, or, you know, the other solution that you got. Should be really awesome, but y equals root 6 minus 2x, which is root 2 times root 3 minus x. No, right? Because it doesn't have the same singularities. I mean, the fact that you're getting it done is, in some cases, more important. So you end up with so if we attempt to isolate y, this is going to end up with a quadratic. Man, that is gross. Yeah, show them both solutions. Just say I don't understand how both could be solved for, like how we could just get both of them. Might be something to talk about. Okay, so this is going to be 8 minus y squared is equal to parentheses k plus or minus x squared over 8. Alright, 8 minus k plus or minus x all squared over 8. It's equal to y squared. Gotcha. So maybe you don't want to ask it like in class, unless you're on a similar topic. So interestingly enough, this is also something similar that happens in other parts of even ordinary differential equations, where you could, in theory, have a second solution, but like how would you know that that particular thing is the solution? Like, sometimes you wouldn't, and there's no real particular reason that, like, this arrangement of stuff is going to be any better of a solution, or you wouldn't necessarily be able to find algebraically that particular solution. You just end up with like a different form. Right. So, in theory, maybe this is just a different form of the exact same thing we've been dealing with. I don't know. It's messed up, man. Yeah, I don't have anything else in here. Particularly alludes to how this uniqueness could, must have done something wrong? Uh-oh. Can be suppressed to first power. Okay. Interesting. Not that one. That one. Alright, let's see. It's alright, my nonsense over here is just getting me in trouble too, so... Yep, no worries. Yeah, we'll see what we can do. So back to this nonsense. I guess Megamorph or anybody else who had looked at this. Yeah, I don't know. So I feel like there should be some reasonable solution, I guess, but at the same time, just like... I don't know where this is gonna go from here. Yep, you too, Syntax. Thanks. Have a good night. I'm trying to think how this is supposed to work, right? So realistically, we kind of want these numbers to match up. And then from there, we want to keep falling back and getting the same numbers in each of the columns, both pluses and minuses. So we're saying that, right, we can have so I don't know exactly how to express this, but we're going to attempt to do something anyway. So we'll take this whole table and just like go up here somewhere. Right, we're gonna take this, we're gonna place it down, and then say, all right, based on this, we're gonna get rid of all that nonsense. Right, we'll take, forget about this, because that's not really going to separate it anymore. There is no separation, it's fine. Okay, so we need to multiply rows 1, 2, 3, 4, and 5. Rows 4 and 5 need to be multiplied by 2 in order to balance out the appropriate terms. So here, this is going to end up being, right, 2, 2. This is going to be a requirement of 120. This is going to be a requirement of 200. This is going to be a requirement of 40 and a requirement of 60 per minute in order to make all of these things. Okay, now, in order to get all of that, in order to balance all of that correctly, this one needs to be multiplied by quite a lot. And this one needs to be multiplied by quite a lot. Well, that's not true. That's only 3. So that's not too bad. Alright, so we take this stuff. Take that, copy it, move it up. Right, we need to multiply row 1 by 3. That needed to be 320. So we need to multiply our screws by 8. My goodness. Alright. So row 3 by 8 and row 1 by 3 in order to balance those two things out. So 1, 2, 3 by 8 is going to make this negative 80 and 320. Okay, and then this one is going to take out that 20. It's going to make 60. And make that 30 turn into a 90. Okay. So that balances this column, that balances this column and that column. So in order to do that, then we have to back up a little more and say, what do we need to multiply our 15 by in order to get 120? So 120 goes, or 15 goes into 128 times. Nope. Hang on. Yeah, it does. Okay. So row 2 by 8. Copy. Okay, so again, this is now out here. We need to multiply 15 on the next one. Row 2 by 8. That's 80 and 40 makes 120. Cool. So that's going to be 120 and that's going to be 120. So this didn't actually require linear algebra or any of that. It's just a little bit of common sense thinking. Okay, so our plates are balanced, our rods are balanced, our screws are balanced, rotors and reinforced plate are balanced. So now ingots, we just need to know how many smelters we need to create all this stuff. It was 30 a piece. Right? Is 210 divided by 30, it's going to be 7. Okay, so 7 smelters. Then that's going to end up being... Ugh. 3 plate constructors. I think 3 to 2, yeah. Rods was 15 a minute to get us to, oh, right. We've got all of these numbers over here. I think, right? Is that going to make it? So what numbers do we multiply by in all these cases to make this happen? So row 2 is the rod constructor, so we need 8 rod constructors. Screws, we multiply by 8 again. Two rotor constructors and 2 reinforced assemblers. Which is going to get us to... No, that's in a minute, right? That's still per minute. Smart plate is 2 per minute. So we only need technically 1. And then the rotor and reinforced... That puts out 5. I mean, we don't even need that. Man. So that's actually like less than 1 of those each. So we're technically good there. Right. No. Yeah, we only need 1 rotor, 1 reinforced. Because that's more than we need. I'm gonna figure this out. Hang on. So, ad break's about to start. I'll just pop it now. Go get myself the drink in the fridge. Need some water. So, we'll see you back in 3 minutes. Stand up, stretch, do what you need, cycle your water, and otherwise, yeah, just see you in 3. Hey, Fizzbuzz. I mean, maybe. And this is only for, like, stage 1 anyway. As soon as I change anything, it's just gonna all be completely shot to hell. I also screwed this up somewhere. So, I have not accounted for the appropriate time. I'm sorry. Alright, tonight we are hashtag not sponsored by Siren, Broken Dream, Nitro Breakfast Stout. Very lactosey. And being nitro, it's very soft. Okay, so here's the thing, right? So I attempted to do linear programming for real, and I ended up with all of this nonsense here. The problem is that when you actually get down to it, there is no constant over in the like in this side. There just isn't one. So I tried doing a row reduced echelon form and got negative numbers. So this isn't working for us. Good news is that I did learn how to do both maximization and minimization problems using the simplex method. So that was kind of fun. I had only ever learned how to teach the maximization method for a bounded area like this. And I just taught myself how to take the like 1 or 2 extra steps to turn a minimization problem like this into a maximization problem like this. So there's this weird thing where you create the dual of the original system, which is called the dual, but it's using the transpose of the essentially matrix that you've created, and then adding in the slack variables and stuff like that. So it was a bit different. All right, so then we said per minute. That's not what I want. The other one. Where's the other one? Per. Ooh, that's fun. Okay, so this does not get us this does not get us 1 rotor. This gets us 4 rotors. That is the per minute cost, not the total cost for 1, which means that our reinforced plate is also similarly messed up. That gets us 5 total, so that changes this number from 1 to 5. So if we want, right, we can keep this essentially as it is, which will cause us to end up with 4 going all the way up. We could get 4 smart plate a minute and have some reinforced plate as extra. Plus one reinforced plate per minute. So So that actually messes up everything above it. But at the very least, right? So only sync a couple of these things here. So this is going to be 4, that's going to be 5. These are still going to be 4s. 4, 4 plus 1, 4. These were 5 per minute. This is 4 per minute. Okay, so like I said, everything above this is nonsense now, but we still need to properly. We need to change this again. So this is 100. This was you. Ugh. Same numbers as below. Don't change anything yet. Minus 30, minus 60, right? 30 minus 60, minus 20 by 100 to get 4 or 5. Okay. So this is going to clear those out. Then, in order to balance things, we need row 3 to be multiplied by, this time it's only 4. And interesting. Okay. And so our plate, row 1, is going to need to be multiplied by 1.5 or by 2. And realistically, we're also making plating that we can walk on. So we're going to need extra plate anyway. So row 1 is going to be doubled. It's going to get us 60, 40. Row 3 was going to be quadrupled. So that's 160 and 40. Okay, then we're going to need to copy all this, replace all the stuff that's up above. Delete that, and then paste in the new one. This is going to get us an extra, oops, down. Plus 1 there, plus 10 here. That's pretty nice. And then we need to change rods, which are minus 60, so we need to multiply by 4. We need to multiply row 2 by 4. So then that's going to become 60, 60. Plus 10 here. All the rest of the stuff's balanced. And then ingots, we need just 120. Okay, so we got it now. This is going to be cleared out again. So we need 120 ingots, which have to be split into two groups. One that's going to get a 60 and another that's going to get a 60, which are two, two smelter, which are linked to plate constructors. Regular plate constructors. Output 20 a minute. Right, so that's going to be two plate constructors. And 15 a minute is 4. Ooh. Two smelters to 4 iron rod constructors. Kind of hope not. It's okay. It's just kind of. It's only slightly unsettling, it's fine. Terrabert! What the heck are we doing here? Right, so I originally was trying to solve a problem within Satisfactory using actual math, and had a pretty terrible time of it. This was also at 3 in the morning this morning, so, you know, somewhere about 21 hours ago. 20 hours ago. I think maybe we'll skip the seance. But the more important thing that we had done here was to try and work out like how many, like what kind of production line I could create within Satisfactory to make smart plating. So last night I had worked on trying to create a production line to make said smart plate, and it worked with some success. But I wanted to make it much more efficient because there was a lot of stuff that was just getting held up constantly. And so I said, all right, let's figure this out. So working backwards, if we want 4 smart plates a minute, actually working from the mid, we said we can create 4 rotors a minute and 5 reinforced plates a minute, which is enough to create 4 smart plates a minute. This is going to end up having 2 assemblers for smart plates exclusively. Right, that can do 2 a minute, so we need 2 of them, and we end up with 4 rotors which go directly into the smart plates. 4 of the 5 reinforced plates go into the smart plates, and then we get 1 extra that comes flying out and we get to store. In addition, we get 10 regular plates a minute, which are going to just be thrown out into a bin, because we are going to use that to build flooring, and so we can expand the factory. So this is going to be pretty good. Working backwards, we said we know how many per minute. Right, we can make 40 screws a minute at the cost of 10 rods per minute. And then in order to scale up, to make sure that we can do the 2 underneath it, to make enough rotors and reinforced plates, we need 160 screws, so that scales up our screw production by 4, which means that our usage of rods needs to scale up by 4. And then when we did that, we said now we have a rod usage of 60, which is a scale of 4 on the rod production, which is going to get us this thing, which now we have to get 120 ingots going through, which is going to be split into 2 smelters, which then one goes to plates, one goes to rods. How many rods per hogshead? Exactly. You want black powder? I get you black powder. Oh, God, I love that character. Anybody who doesn't know, it's a guy from Critical Role. Matt Mercer produced this character, and everybody was like, I love him. We need to visit him every time we come to the city. He was basically like wiry white hair that's been burned off in places. He produces black powder, and no one else knows. Essentially, nobody knows what black powder is. It's like a brand new invention. So he's the wild scientist who has, like I had done here, literally lost parts of his fingers in the creation of this stuff. At some point, he says, how many hogsheads do you want? And the guy's like, just the one? And he grabs a literal hog's head off the ground and starts shoveling it in by hand. And the guy's like, don't do that. Oh. Also fair. Okay, so this is going to be interesting. So the 2 plate constructors, we're going to have one feed directly into, what is that, rotor? No, reinforced, of course. Alright, one feeds directly into a reinforce assembler. And one that splits into... one goes back to the reinforced assembler. Or are there 2? Actually, I don't need to do that. I can just do storage. There's one reinforced assembler, and there's one rotor. And in between all of these, we end up having a storage bin. So it can dump as many as it wants in. And then in theory, if everything is balanced, then the same numbers are going out as are coming in. And then everything is balanced and everything is fine. So instead of waiting for like the production line to move, it's just going to spit everything out into a giant storage bin. And then keep filling the storage bin until either it's full or it's empty. Well, okay. Keep filling it until it's full. In theory, all of this should be balanced such that we don't have anything filling. So what we're going to do is we're going to store everything. Right, the plate constructor will have 2. it just goes to storage, right? But then we're going to take 10 per minute whenever we need it. So we're going to end up having stacks of 200 every 20 minutes. And we'll just keep taking them. Alright, the 4 rod constructors spit out into bins. We have 4 screw constructor. Which then the screw constructor how many are in each bundle of the screws? Nope, that's not what I wanted. Other way. There we go. Screws. Got screws. What? I'm hitting the button a lot. Alright, screws. We end up getting 40 a minute. Ugh. It's 1.5 going to reinforced. Lovely. Manufacturer requires 10 motors and 20 modular frames, 50 plastic, 50 cable. Probably want to make 2 of them. It's just so I can make the materials for the next space elevator delivery. Yeah. Yeah. Understandable. Although, since now I have a parachute, I feel pretty good about building like multi-story complexes. Okay, so like 2.5 of those. Right. So like 1 goes to the reinforced. Okay, 1 goes to reinforced. Oh, no. Okay, 1 split. And 2 go to rotor. I shouldn't do that. Hang on. Right. 2 go to the rotor assembly. 1 splits in between. And then 1 exclusively goes to reinforced. This is not confusing at all. It's fine. Right, and then the 1 reinforced and rotor assembly will combine into a storage. No, don't do that. They are themselves separate, which they combine into 1 small plate. Smart plate, Jesus. 1, no. They split into 2 smart plate assemblers. Right, I already wrote that. It's here. It's right there. I should know that. It's right there. Right, so then the reinforced assembler will split. It's dumb. Why did I do that? I would prefer multi-story simplices, but I can't increase the number of dimensions I have. I only have 3. Oh no. Just think about it, Megalomorph. As soon as Miyagakure comes out, somebody's going to create a Miyagafactory. You just have to step through 4 dimensions. You can create new space in the exact same 3-dimensional space, but it's displaced in the 4th dimension. Oh man. If there's anybody who's read The Long Earth, right, you know what I'm talking about. Yup, I would not have the coding ability to even remotely touch that. It's kind of interesting. So the premise of The Long Earth is that this is written by Terry Pratchett and Stephen Baxter. The premise of The Long Earth is that there's this gadget which becomes widely popular, especially among like teenagers, called a stepper. So 6-dimensional matrices, yeah. So the stepper allows you to go between this Earth and an Earth that is one come on. Yep, it's the beer talking. Damn it. Not continuous. Right, discrete. That is one discrete step in a different direction. Right, it is one dimension over, essentially. And so, you know, whatever discrete step it is, it shifts your perspective such that, like, the Earth is a different Earth, and almost the exact same things happened on that Earth as on this Earth. And then from there, almost exact same things happen on the next Earth and the next Earth and the next Earth. You could go in either direction from Earth Prime, right, where we are. But the problem is that you're not allowed to take iron, like all iron except that which is in your hemoglobin, like all iron, just as metal plating and stuff like that, gets stuck in your previous Earth. So like you will step to the next Earth, and then like your belt would fall apart essentially because it's got an iron buckle. So if it's a steel buckle, you'd have carbon holding your belt together. And like, you know, your watch doesn't work anymore, or all this other stuff. So, and the other problem was that the original, like, especially teenagers who passed this schematic around for the stepper. They did it all kind of surreptitiously on one particular day, and then they were like, everybody do it. Everybody jump now. And then, like, as soon as they built it, they tried it. And when they tried it, they'd step one Earth over. But a number of them were in buildings which don't exist on the next Earth over, so they fell to their massive injury or death in many cases. Even those who were, like, if you were just, like, stepping from this Earth to another, like, a lot of places have been affected by humans, and so, like, places had been, like, excavated, and, like, if you're in one of these excavated places, it actually doesn't allow you to step if there's something physically in the way, but it could also potentially shunt you slightly, and getting shunted is also not a pleasant experience. But it was a real fascinating exploration of, like, the potential of this, like, brand new technology, which is, essentially passed around on through quiet methods that teenagers know. At least on day one. So they called it Step Day, and this guy, like, created this object which allowed people to step into the next Earth. And when they did it, it's also powered by a potato. Because you needed, like, the correct amount of voltage to get through, and what do you know? You can make a potato clock out of it, and it produces the correct amount of voltage. So there's this one guy, I think his name was Joshua, who ended up, like, seeing everybody step, and then had to, he ended up making, like, hundreds of trips by himself to the next Earth to collect all these injured kids and bring them back. And, like, he's hailed as this massive hero and stuff like that. And there's some interesting story behind him. He's got something special going on, so he's not just, like, some random hero. Oh, and some people reject the step, so, like, their body makes them feel extremely nauseous every time they try, so they just can't do it. Okay, I need to, let's take a print screen of that. Get it into, hate doing it, but Paint. Okay, and then we'll hang on to that picture. We're going to start up Satisfactory and actually implement this and see how it goes. Because, in theory, this should work. Satisfactory. Uh-oh. Is this also not working? Cool. It appears that my left clicking is not working in Steam either. What the actual F? Top. What do we have that's messing us up? So Firefox, we got 20 gigs of virtual memory being taken up. 32% of our CPU. That doesn't sound right, now does it? Discord, 1,161 virtual gig. Also doesn't sound right. which is fascinating because our Discord is closed. How did that happen? All right. What is going on? I can open other stuff with left click, but I cannot actually do anything in Steam or in Discord. I can click just fine on Firefox. I don't like this. There is something seriously wrong here. Alright, so I'm going to quit Firefox, which means that the music's going away. Awkward, I know. Let's see, what else is here that could possibly be messing with this? Anybody else has any ideas, let me know. It could be OBS, in which case that's a big problem. Alright, can we... This happened very suddenly. Let's see. Can I? Yes. Okay, I can do do things just fine in OBS. I can do things just fine in Terminal. This started when I Alt-tabbed between a game in Steam and Windows, I think. But that game is closed, so I don't know what the issue is. What's causing problems? Like I said, if anybody has any ideas, let me know. Like I said, it's not really, it can't literally be Steam. Can't literally be a bunch of stuff. Okay, is Steam closing down? Yes. Cool. All right, come over here. We have now closed and use the console, open Steam. Nope, can't do it. Okay, that's fun. I can't hit anything. I can't open anything in. Can't open anything in Steam. I can't left click. It's ridiculous. All right, we may just have to close anyway. Okay. And you know what? If we have to close the stream, that's fine. We can implement next stream. Okay. Yeah, we'll implement next stream. We're going to head on over to, come on, don't do this to me. No, okay. It's clicking just fine. We'll head over to Don, who is currently doing math stuff, and looks like he's still going. So we'll see you all on Tuesday for mathy stuff. Next Friday, oh, nope. Tomorrow for spooky stuff. We are doing Spooky Sundays, and tomorrow I want to work out the issue I'm having with I want to work out the issue I'm having with Epic, but I don't know that that's going to happen. So worst case scenario, we will go back to Slay the Princess and figure out what's going on there. I just need to restart my whole computer and figure out what the hell's the matter with this thing. Optional, also, we might be able to do Control, which was very much fun. I'm done with the game, but nonetheless, there's always little things to do. There is also No Time to Explain, which may not exactly be horror, but, you know, it's something. And we've got a few other things that might work. I'm going to have to look into a couple of other pieces on my horror list and see if we can get something creepy. Anyway, hope you all have a good night, and I'll see you all tomorrow for Spooky Sunday. All right, my name is Obi-Wan Pez, and this is N Simplex Pachinko. Have a good night.